Hello, everyone. I'm here to present our work on developing a single-agent urban coastal adaptation model within the viable modeling framework. I am Shubhankar Sengupta from the Climate Service Center, Germany, abbreviated as JERIX. My co-authors are Dr. Dmitry Kovalevsky and Professor Jürgen Scheffran. The model we are presenting was developed under the MOOCs project carried out at the Helmholtz Institute for Climate Service Science, which is a cooperation between JERIX and University of Hamburg. The project aims to model the complex dynamics of coastal cities under climate change in order to plan adaptation strategies and support coastal climate services. Throughout, 4 varied modeling approaches will be utilized, and our current model is a demonstration of the first approach, agent-based modeling. One of the primary research questions of this project and my dissertation is, what can these different modeling paradigms offer in terms of representing the complex interlinked systems of urban coastal environments? So what advantages or drawbacks does each approach have, and what synergies can be found by employing them in parallel? The first of these approaches we examine is agent-based modeling. This modeling approach utilizes individual actors known as agents, which act independently by interacting with the system they inhabit and any other agents that may be present, following certain decision rules to achieve their separate goals. Compared to more macro approaches, ABM offers a deeper insight to how small-scale changes affect an overall system. As a result, we often find that implementing basic rules leads to complex emergent patterns. This makes ABM an ideal paradigm to model systems such as the coastal city. For our agent-based model, we build upon the viable framework developed by Professor Dr. Jürgen Scheffran. This modeling framework is an application of viability theory, which describes agents pursuing goals while confined to a limited space of action that is termed as their viability domain. These agents display adaptive control, which means they act based on defined decision rules to respond to a changing system. They possess limited knowledge and resources and move in the direction of local maxima of value by investing these resources into pathways of action. This schematic demonstrates how the agent acts on the system using these resources with the goal of maximizing its value, while its capability puts an upper bound on its action. The system state changes in response, and the agent adjusts their action path based on the new state. Viable offers a dynamic generalized ABM framework of agents within a bounded space of action that can be applied to a broad selection of contexts, making it a good fit to answer our research question. Our model uses a single agent variant of the viable model and implements it in an urban coastal scenario. We represent our system in a non-spatially explicit form, an arbitrary area designated as the coastal city with a certain fraction lying on the coast itself and thus vulnerable to climate change-induced damages. Over the course of the simulation, gradually rising sea levels threaten the coastal territory unless sufficiently developed defenses are present. We represent this in terms of the height of the defenses, which is the amount of sea level rise that they can effectively protect from. We dictate a minimum threshold height, which is how much higher than the sea level the defenses need to be to result in zero damages. Faced with these potential damages, the city planner agent has 2 options before it to mitigate them: developing the city's coastal defenses, which when undeveloped deteriorate over time, or as a more extreme measure, relocating coastal territory inland. It can allocate resources from the income generated by the city towards these 2 pathways. This means that agent behavior can be represented by 2 control variables: the amount of capital it invests towards overall mitigation, and the fraction of this investment that it allocates to each pathway. The agent selects the control variables that result in the maximum value. This value is the balance between the agent's positive and negative utility, or disutility. The positive term comes from the amount of resources consumed, that is, the capital remaining after investments have been allocated. The negative term depends on the damages sustained by the city, which, going by the common definition of risk, is a function of hazard times vulnerability. The former is the excess sea level over the minimum threshold height the coastal defenses can protect against, while the latter is the vulnerable coastal fraction of the city territory. As per the viable model, at every time step, the agent calculates the values of its control variables that correspond to the maximum value for the agent. It then adjusts these parameters in the direction of these optimal values, taking C, the investment amount, and R, the investment fraction, as the control variables. That means that at every time step, the agent first calculates C asterisk and R asterisk corresponding to the maximum value, and then changes its own controls by delta C and delta R, dictated by these equations. In this process, the agent is limited by a fractional variable termed as its adaptation rate, representing its adaptive capability, K for delta C and alpha for delta R. This means the agent cannot immediately shift to the optimal state. Another limiting term in the first equation slows down the agent's adaptive rate as it approaches the upper and lower bounds of investment. Regarding the dynamics of how the system state corresponds to the agent's actions, the investments of the agent can lead to an increase in the height of coastal defenses H, which depreciate over time unless they are invested in at the rate lambda, or a reduction in coastal territory S. CH is the actual investment put into developing coastal defenses, and CR is the amount put into city relocation, while KH and KR are the efficiencies of investment for each pathway. At the end of the time step, if the sea level exceeds the effective height of the defenses, then the resulting damages are calculated as shown. These depend on the amount of area that is coastal and the amount by which the sea level exceeds the threshold height H asterisk. The function f here scales linearly with this excess height. This is a schematic representation of the main processes of the model, summarizing the previous slides. The agent acts on the system through its investments into the two adaptation pathways, which in turn affect state variables and eventually agent value. So when it comes to analysis of the model, we can divide our system state and agent variables into the independent ones representing the input and dependent variables representing the output. The independent parameters set the initial conditions for the simulation, such as the amount of coastal territory or the starting pattern of agent investment. They can also include parameters outside of the agent's control, such as the efficiency of investments in both pathways or how sea level changes over the course of the simulation. The dependent parameters together represent the output of the model, including where the agent invests resources, how the coastal defenses develop over time, and how the urban distribution between coastal and inland territory evolves over time. This is the graphical interface of the model during a typical simulation. The dependent variables are tracked with graphs, while the initial conditions are set with sliders. The rate of sea level rise can be set to various modes. We also introduce climate shocks. These are extreme sea level events that last for short periods of time, spurring the agent to respond and getting more frequent and severe as the simulation progresses. As we see from the sample simulation, our model agent behaves in a highly reactive manner to the dynamics of the system. It stays at a default investment allocation for as long as damages are zero. As soon as the rising sea level crosses the threshold height for coastal defenses, the agent shifts resources towards building up these defenses. If this proves sufficient, the agent returns to its default mode of behavior and investment towards adaptation drops. Since the sea level continues to rise while defenses deteriorate over time without investment, the agent ends up closely following the trend of sea level rise, investing only when it suffers damages. After a point, when the capital is not enough to build sufficiently high defenses, the investment ratio shifts heavily towards city relocation, and the city's coastal areas are subsequently relocated inland. Thank you for your attention. We would be glad to answer any questions or feedback.